Hello, and welcome to my channel. In the previous lecture, we have discussed that at 0 degree Kelvin, intrinsic silicon crystal bar behaves as an insulator due to the absence of free charge carriers. We also discussed a very important equation which provides fundamental intuition in the basic physics of semiconductor. The equation is Ni equals 5.2 into 10 raised to power 15 into t raised to power 3 by 2 into exponential power minus Eg by 2 into kT. According to this equation, carrier concentration or density at 0 degree Kelvin is 0, as we have already calculated in previous video. Now, we are interested to know what will be carrier concentration at room temperature in intrinsic silicon bar, so we may easily analyze why we calling intrinsic silicon as poor conductor. For equation 1, first we will convert band gap energy Eg from electron volt to joules. As 1 electron volt is equal to 1.602 into 10 raised to power minus 19 joules, so Eg in joules will be 1.792 into 10 raised to power minus 19 joules. Plugging all values in equation 1, we will get Ni equals to 1.08 into 10 raised to power 10 electrons per unit volume. The figure, 10 raised to power 10 is high, but when we compare it with copper which contains 10 raised to power 28 electrons density at room temperature, by comparing these two numbers, we can easily conclude that intrinsic semiconductor is a poor conductor at room temperature. Now, a question might come into your mind that, if we increase the temperature, we can increase the conduction of silicon, but it is a very impractical approach as higher temperature is not a desirable property in electronic devices. But wait, there is another solution by which we can increase carrier concentration. We add impurity in intrinsic semiconductor, and now that semiconductor is called extrinsic semiconductor, and this process is known as doping. Before discussing the doping, it is necessary to have a look at the importance of hole. Remember that hole is just a vacant position which shows the absence of an electron in valence band. As we have seen in energy band diagram of semiconductor, an electron jumps from valence to conduction band by applying external heat energy. Now, this vacant position represents hole. Remember that hole is not a particle, it's just a vacancy which can be filled by other electrons. Now, for an intrinsic semiconductor, electron density is equal to the hole density as the number of electrons moved to the conduction band. The same number of holes will appear in the valence band. Holes have equal importance as electrons, however, electrons have higher mobility over holes. This distinct advantage is very important as it leads to fast switching speed, especially in transistors, where they will switch on and off more quickly. Let's discuss the doping. Doping means to add impurity into intrinsic semiconductor to alter its electrical properties. We add two types of materials into intrinsic semiconductors, pentavalent and trivalent materials. Pentavalent materials have 5 valence electrons and they are added to increase the electrons concentration. While the trivalent doping agents have 3 valence electrons and they are added to increase holes concentration. By adding pentavalent materials into intrinsic semiconductors, we get N-type semiconductor, and with trivalent addition, we get P-type semiconductor, which are the fundamental to the foundation of semiconductor technology. These two types of materials form the basis of most semiconductor devices, including diodes, transistors, and integrated circuits. In the next lecture, we will see how we add impurity into intrinsic semiconductors and how the p-n junction is formed. Thank you for watching this video. Stay tuned and subscribe.